All right, in this lecture I'm going to help you solve some problems in your binder. And I'm going to focus on Lab Activity 7 involving hotspots. We'll look at both Yellowstone National Park, we'll look at some geysers, in particular Old Faithful, and we'll look at Hawaii. And Activity 8, we'll talk paleomagnetism, and I'll help you do some solving of the calculations that solve for the rate of plate motion. So here goes. So if we look at a hotspot geology map, we will see that a hotspot is a portion of Earth's surface that experiences volcanism through rising mantle plumes or some other cause. Hotspots are unique and can be found great distances away from plate boundaries. So up to this point in this semester, we've learned that volcanism and earthquakes are very common, take place around plate boundaries. But here we're looking at volcanism that takes place within plates, where Yellowstone has a continual upward flow of this mantle flow that's moving upwards, and it's actually able to generate these conditions or characteristics of what we call hotspots. And once we have this mega eruption, it actually can form a caldera. More to come on that. And along with this region of Yellowstone, we also find geysers, hot springs, fumaroles, and mud pots. So different activities are associated with Yellowstone National Park. Here we can look at how volcanic eruptions are ranked. They're ranked on a scale of 1 to 8, called the Volcanic Explosivity Index, or the VEI. The sizes of these circles here in the picture represent the volume of ash and ejecta. So we can actually see here that Yellowstone eruptions have been these mega scale eruptions, and they really pale the comparison of how large Mount St. Helens was. It's just kind of a tiny volcanic eruption relative to the Yellowstone caldera forming eruptions. So here we can see the supervolcano. Here's kind of a cross-section of it. That during this eruption, rock is pulverized into a powder, and this powder is transported by the winds in the atmosphere. It eventually falls out. So the Yellowstone supervolcano is a complex geologic structure. It has hotspot geology, where you have this mantle plume several miles beneath the Earth's surface. The conditions support geyser activity. We have caldera series, what's called a hotspot trail. We'll look at a map here in a moment. And also forms a composite cone volcano, alternating layers of lava and pyroclastic material. So let's explore this a little further. Rhyolite partial melting occurs as basaltic magma sweats out the light elements. We've studied Bowman's reaction series, that the lighter elements have lower melting points: quartz, muscovite, mica, and K-spar. So rhyolite, remember, it's compositionally equivalent to that of granite. So rhyolite is associated with violent eruptions, high viscosity magma, and high silica content. The gases build up and are released in energetic bursts at times. So when we look underneath Yellowstone, we have these ingredients, we have these conditions that are driving, let's just say, the unique conditions of Yellowstone. Here we can see the hotspot trail, right? So Yellowstone National Park, northwest corner of Wyoming. It's got this mantle plume, or the hotspot itself, and North America is migrating over it. So the hotspot trail, this reflects how North America has migrated over a fixed hotspot. Such intraplate volcanism remelts out silica-rich rock, leading to caldera-forming eruptions. These are all calderas. And we can see the trail of the direction of which North America has moved over, or migrated over the hotspot beneath North America. So these are mega-scale eruptions. The cubes represent the volumes emitted at Yellowstone's 3 major eruptions. As you can see, they dwarf the 1980 eruption of Mount St. Helens in Washington State. So here we have 3 mega-scale eruptions here. And here's where we can find the fallout zones, calderas and ash fallout zone. There have been 3 colossal eruptions that led to calderas. Each has occurred in about 600,000 year increments. It has been about 600,000 years since the most recent eruption. So what is a caldera? Well, caldera is a sunken volcano, right? Due to the lowered pressure after the eruption, due to the open cavity that has lower internal pressure. In other words, it's no longer able to hold up the material above it when it has kind of an empty magma chamber after the eruption. The ash fallout. This is the volcanic debris eventually falls out of the atmosphere. Prevailing winds influence where it falls. So you can see where these have fallen. It's not only just in its area, but it falls out in the direction of the prevailing winds. So here's a map. This is if we were to experience a Yellowstone National Park mega eruption, supervolcano eruption. Here, pretty much anything in this zone would be dead. Here'd be your primary ash fallout zone, and this would be a secondary ash zone. If I compare this just to Mount St. Helens, you would see, look how large Mount St. Helens was. Remember, we're talking about volcanic eruptions on a much, much, much larger scale. So if the Yellowstone National Park supervolcano were to erupt, planetary climate would be affected dramatically from 10 to 100 years. The atmospheric debris field would transport the aerosols and the fine dust all over the Earth, decreasing the net solar input to Earth. Another feature that takes place at Yellowstone, it involves geysers. It's simply the hydrogeology, the gaseous eruptions, or the water vapor. That in this case here, we have, we can talk Old Faithful, we can talk about the plumbing system. So be sure to catch up on these videos here. So what are geysers, and how does Old Faithful at Yellowstone work? Well, geysers intermittently erupt jets of water. At Yellowstone National Park, geysers eruptions are initiated when water in a geyser conduit starts to boil vigorously. The expansion of the steam powers the discharge. Expanding water molecules under these conditions leads to about 1,500 times the volume, driving tremendous upward force, or pressure in this case, right? Pressure is simply a force divided by an area. So the geysers requires temporary overpressures created during repeated cycles of reheating by superheated waters. A critical requirement for long-lasting activity of geysers is the maintenance of the appropriate permeability within the geyser conduits relative to the surrounding rock. So let's make sense of that in these pictures here. The eruption takes place where we have water flowing into a region that's being heated by some source. And as long as you have this opening, this conduit system, like a plumbing network, you're going to have the conditions, right? The conditions that are going to be conducive for geyser activity. So why does Yellowstone National Park have so many geysers? Well, there's three primary characteristics necessary for a geyser. You have to have groundwater, or essentially a recharge zone. Water has to be able to refill. You have geothermal heat, right? You have to have a source of heat, right? Yellowstone National Park, we've got hotspot volcanism, kind of a semi-permanent fixture. And you have conduits that are airtight, providing the plumbing system as an outlet on the Earth's surface. Yellowstone National Park has all of these characteristics. Yellowstone contains about half the world's geysers, and the largest is not the Old Faithful, even though it gets the most recognition. The largest and most powerful is actually Steamboat Geyser, seen in this picture here. So let's look at a cross-section of Yellowstone National Park, right? So we can talk Old Faithful and some of the other geysers. Here's what we have going on. We have this flow of groundwater, we have our heat source, and we have fractures. We have fractures that reach the Earth's surface. And when you put all of these conditions together, just as I mentioned prior, you have these three conditions, you're going to have geyser activity. It is consistent with hotspot volcanism. So in this case here, as soon as you have your eruption, right, if we have an Old Faithful geyser eruption, water is going to refill, it's going to reheat, and it's going to have its conduit system. So it's going to continue to exist as long as you have all three of those conditions taking place simultaneously. Here's a data set that I found interesting, how the eruption times have changed since, say, the mid-1960s until today. So this is called a box plot showing the increase in eruption interval of Old Faithful from 1960 to the present. And you can see that the time is actually increasing between eruptions, or the average time. So this is the interval between eruptions, right? These are in minutes. So today it can be as up to 90-some minutes, where historically it's been in 60s. So notice your time, your slope is telling you that the time is taking longer between interruptions. And there's a lot of features or factors that can influence that. Moving on into Hawaii and the Hawaiian Islands. So we have this plate, Pacific plate, that's moving over a fixed hotspot. These mantle plumes are providing the steady diet of magma. And here we have the Hawaiian Island chains formed. Well, when I look at this on a geologic map, we can see that hotspot volcanism is directly tied to plate tectonics. That the island chain of continued eruptions from volcanoes actually come from the Pacific Ocean floor. That's where these islands actually form from. So when we look at it from a larger scale, you can see the Emperor Seamount chains. These were just ancient Hawaiian islands that today they're just below sea level. That this entire Seamount and Hawaiian chain system are indicative, or telling you the direction in which the Pacific plate was migrating over this hotspot. So the direction of the islands are northwest, right, today. But they were once north as the Pacific plate moved over the stationary hotspot. So moving on into paleomagnetism. So here's a picture depicting what's going on here. So oceanic crust, basalt, contains iron-bearing minerals. As the magma crystallizes or solidifies, the iron minerals solidify oriented in the existing Earth's magnetic field. Over Earth's history, the magnetic poles have switched, and the Earth's oceanic crust records this. We can call normal polarity, we can call kind of reverse polarity here. And the further we move from the ocean ridge, the older the oceanic crust, and you pretty much get a mirror image on one side to the other side. So paleomagnetism is a way in which you can use the ancient oceanic crust to determine the Earth's magnetic field. And the magnetic field over time has switched directions. The magnetic North Pole has not always been where it is today. It's actually flipped back and forth. So we call it normal and reverse polarity, or reverse fields. So we can see how the dark and light bands reflect the orientation of the Earth's ancient magnetic field, right? Paleo means ancient. And we can see that either direction from the ocean ridge moves at about the same rate. So we get this kind of, this side looks a lot like this side. And here's an actual picture from the ridge axis that you have in your binder you can look at. And you can actually date these dark bands over here are roughly the same, or exactly the same age as these bands over here. So you have this timeline. You have oceanic crust, which is igneous rock, that you can radiometric date. So we can put a timeline as to when the Earth's magnetic field was switching and flipping. And we can also calculate the rate of plate motions using this information. So the distance from Kauai to the Big Island, it's kind of more the center here, is about 570 kilometers or 350 miles, depending on precisely where you measure from. So we can ballpark about 570 kilometers. And you can see that this island chain, if we can assume that the rate has been relatively stable, then we can actually calculate the rate at which it moves. So in your binder, I have you solving some problems, and I actually created a video that you're going to go and look at this picture here. You're going to start taking a look here at how this ocean ridge, or in this case here, we have a divider here. We have a divergent boundary forming. And over time, they're moving apart. Either side is moving in opposite directions. And so you're going to be making sense of these letter C's here and letter W's. And this picture doesn't come in very well. And then you're going to answer these questions. And the second part of this is you're going to look at this picture here, and then you'll answer these questions. And lastly, you'll look at the Hawaiian Islands, and we can determine the rate of the Pacific Ocean. And the Pacific rate of movement is actually a lot faster than other locations. That not all plates are moving at the same speeds. And last but not least, you'll answer these questions here. You'll be able to answer these questions and do the calculations based on the scale of the map itself. And here's the video in which I will show you how to do it. So make sure you watch this, and I'll show you how to do all the math to it. And to end this lecture, you'll see that lithospheric plate directions and velocities, that they are not all moving at the same rate. That here you can see that the Pacific plate, notice in red here, is moving at a different rate than, say, the continents. So if you look at the magnitude or the size of these vector arrows, not all plates are moving at the same speed, and they're all moving in multiple directions simultaneously. There's a lot of interaction with these plate boundaries. So hopefully that makes sense. You'll be able to do the calculations and the solving, and that should have helped you with your binder. Good luck.